Participants, he is Professor Chandan Bose. He has joined from the University of Birmingham. He is a faculty member there at the Aerospace Department. And he is presently our principal investigator for the OpenFOAM team of FOSSEE. So over to you, Professor Chandan. You can start your session.
Hello, everyone. So I'm Chandan. I'm an assistant professor of aerospace engineering in the University of Birmingham, UK. And in this brief session, what my objective is to basically demonstrate to you what are the different features for particularly dynamic meshing or moving body problems related to external aerodynamics, but not only aerodynamics, it can be used for any other applications. And what are those features that are available in OpenFOAM which you can use to simulate your own moving body problem. Moving forward, I lead a group which is named as Bio-Inspired Fluid Structure Interaction Laboratory in the University of Birmingham. And we are basically interested in different aeronautical and also in general fluid structure interaction problems. So some of the topics that our group actively focuses on are bio-inspired microaerial vehicle, unsteady aerodynamics, fluid structure interaction, aeroelasticity, and in general, broadly computational fluid dynamics. And we have basically multiple funded projects going on currently, mostly funded by Royal Society, University of Birmingham, EPSRC, etc. And mostly, as you can see from the ongoing projects, we are very much focused on using the knowledge of fluid structure interaction and learning from nature how we can implement these natural mechanisms into the futuristic aerial vehicles that are basically the primary focus of our group. And among all the research interest, the one which is very close to my heart is basically bio-inspired flapping. So currently we are focusing a lot to understand how the naturals, birds and insects actually use bio-inspired fluid structure interaction to actually increase their aerodynamic efficiency, and what is the role of very much unsteady nonlinear vortex dominated flows in the underlying increment of aerodynamic efficiency. So this is the simulation that you can see, that which we are actually developing a GPU enabled a fluid structure interaction solver which can actually aim to simulate hundreds of such butterflies flying together and understanding their nonlinear physics. Now, hopefully you have got a brief idea about my research interest. Now, before I go into the actual topic, just to assure you that I am the right person to give this demonstration to you. So I am working with open source code developments, including OpenFOAM from my PhD days, more than 10 years now. I have been given the responsibility to lead the FOSSEE OpenFOAM project, and I'm member of the OpenFOAM Technical Committee for Documentation and Tutorial, and currently an editor of OpenFOAM Journal. And different works from our group have been featured, including in OpenFOAM Journal cover. So as you can see, these are two of the covers that features our work in the OpenFOAM Journal. Now, with that brief introduction, let's basically try to look into the features of dynamic meshing within OpenFOAM. And as you have already got the idea from the rest of the today's session, that OpenFOAM is a very broad code library that can be used for multiphysics simulations in a very broad term. And fluid dynamics, heat transfer are just one subsets of these libraries. You can do many other things such as magnetism, phase change, etc., etc. Now, this particular topic, which is dynamic meshing, is actually applicable to any of these themes or any of these particular solvers that you want to use. So they are not limited to aerodynamic solver. However, for the focus of this talk would be more like external aerodynamics problem, because I guess the audience is more interested towards that. And even within dynamic meshing techniques, we have multiple different type of algorithms or approaches by which we can actually implement the dynamic meshing to move a body or a structure within our computational domain. So among all these different algorithms, I would mostly focus on two majorly. One is mesh morphing, another is overset meshes. But I will just give you a glimpse about other type of dynamic meshing techniques such as moving meshes, sliding meshes, adaptive mesh refinement. Now, what are dynamic meshes actually? So, and why do we need them? So dynamic meshing strategy allow the mesh motion. As I told that it enables us to implement a moving body simulation for whatever application that we are interested in. And now to allow this mesh motion, we have to modify the governing equation of our problem. And these kind of approaches can be actually considered in different kind of algorithmic framework, such as one is arbitrary Lagrangian Eulerian framework, where mostly we will implement this mesh morphing type dynamic meshing, where you can see this is my scalar transport equation, and in the convective term of our governing equation, we have to modify the velocity term to a relative velocity term by including the mesh velocity UG here. So that's basically the underlying mathematical change that we need to do to incorporate this kind of mesh motion. Now, as I said, that this mesh motion can be actually implemented by deforming your mesh. That is one of the very popular approaches, which is called morphing. We can do this by adding or removing new cells in terms of remeshing our computational domain. We can use sliding of one mesh region over another mesh region, or we can actually use overset meshes, which means that we use multiple different type of mesh at the same time, overlap with one another, and then apply the motion to one of these mesh zones, and then interpolate the solution back to the background Eulerian mesh region. Okay, so here the take-home message is that dynamic meshes should be compatible with all type of physical models. So it is not limited to only solvers that we use for fluid dynamics or heat transfer. It can be used, the same framework can be used for any type of multiphysics problem. Now, dynamic meshes are useful for, as I already told, to incorporate prescribed body motion, where we want to simulate a moving cylinder, for example, very benchmark problem that you can see. And you can see in the left where it is having a mesh morphing, you can see as the cylinder is moving up and down with a prescribed velocity or displacement, you can see that the cells around them are actually getting deformed to accommodate that motion. And that is basically called the mesh deformation or mesh morphing technique. Now, there can be other types such as rigid body motion, fluid structure interaction. And how fluid structure interaction is different is that the body motion is not prescribed. The body motion is calculated based on its interaction with the unsteady surrounding flow. And then last but not the least, we have mesh refinement or unrefinement, where we consider a particular scalar variable, and then accordingly to capture the change in that particular scalar variable, we can refine the mesh locally or unrefine the mesh by actually creating, as you can see in the rightmost part, creating new cells or dividing the cells into much smaller cells. All right. So that is called the adaptive mesh refinement. And the middle, you can see, which is named as AMI, it is called arbitrary mesh interface technique, where you can see, I will come in more detail, but here in this case, we use the sliding technique, where we have multiple different mesh regions, and one of the mesh regions slides over the another type of mesh to incorporate the motion, such as here, it's a pitching airfoil. All right. So going forward, the next one, as I basically mentioned briefly, that OpenFOAM also has a overset mesh capability. And that is actually can be seen in the animation in the rightmost part here, where you can see that the same problem of the pitching airfoil has been implemented in three different approaches. So the first one is arbitrary mesh interface, where you can see that the one region of the cells close to the airfoil is rotating by sliding over the other type of outer cell region. And then middle portion is where it is deforming the cells, which is mesomorphing. And the rightmost part, you can see the overset where we have two different disconnected meshes, which is the first one. The upper mesh region is actually moving over the background Eulerian type of mesh. Okay. And then the solutions gets interpolated at the interface of these two mesh region. Okay. So how to set up this dynamic mesh cases, so that should be your first query, right? So now you have probably have done different tutorials with stationary bodies or some sort of lead driven cavity or channel flow problem. You know how to use different solvers, how to set up the different flow condition, such as by changing their viscosity, velocity, changing boundary condition, etc., etc. But if we want to incorporate this dynamic meshing technique, what additional setup requirement is there for an OpenFOAM simulation? All right. So the first one is that these dynamic mesh motions are actually they are controlled by different code libraries that are already written within OpenFOAM framework. So we don't have to code it separately, but we need to call those functions and then prescribed the motion, whatever we want to incorporate in terms of the motion of the body. And the file that we need to actually include additionally in this case is called the dynamic mesh dict. Okay, it's a dictionary file which actually declares and defines the motion of the body, and it should be located within the constant folder. I hope that now you are clear that in the general setup of the OpenFOAM cases, we have three different folders. One is zero, one is constant, one is system. Now the constant folder where we locate different flow properties like transport properties, turbulence properties, and the mesh directory, which is called polymesh. There you have to include another additional dictionary file, which is called dynamic mesh dict. Okay. Now, for moving body simulation, as I've already told, you have to assign a motion type. Okay. And that motion type has to be associated with either a patch, which is a boundary, or a cell region, or it can be associated to the whole computational domain itself. So I'll show you examples for all these three. Now, for example, going back to the animation, just to make it clear to you, in the first problem, which is arbitrary mesh interface problem, we assign this motion to actually a whole cell region, right? Because we are rotating the whole cell region into the inner part of the motion. Okay. And that can also be implemented in a different way by assigning this motion to the patch, which is just the airfoil patch. Okay. So that's why you have to take into account that you can do it in different way. One way of defining this motion type is either to assign it to a patch or to a cell volume or cell region, or in a different case, different problem, which I will come in a while, we can assign the motion to the whole domain. The exception is adaptive mesh refinement, because in this case, we have to set a refinement criterion that what is the physical quantity that we are trying to capture, and that will be in terms of a scalar field basically. And then we have to set that refinement criterion within this dynamic mesh dict, so that then leads or tells the code to refine the cells locally based on the change in that particular physical quantity. Okay, now that we know where to actually define different motion, the another important part that needs to be changed in this setup, that is the boundary condition. So as you know that within the zero folder, we actually have different boundary condition and initial condition defined depending on whether it is a wall, whether it is a patch, whether it is even within walls, if it is a slip wall or no slip wall, etc., etc. Right? Now, for example, for the previous example, if you want to give the motion to the airfoil, which is a patch, if we want to mention or prescribe a motion type to that patch, the boundary condition has to be changed. Okay. So that, even though that's a wall, that has to be changed to the type of moving wall velocity or calculated type of boundary condition, so that the code knows that the velocity on the wall gets changed or as the wall moves, right? Like the airfoil which is pitching. So just to show you schematically, where does this change? So in the whole tutorial case structure, you can see that within the constant there is polymesh and then other properties, system 0, and within 0 you have basically the initial and boundary condition given for pressure and velocity and other fields if there is such as temperature. Now within constant, we have to include this particular dictionary file that I told, which is dynamic mesh dict. Okay. Now, I'm not going into the details of the source code because I don't think most of you have the background or I have the time to do that. But if you really want to see where the source codes are located, or if you want to take the source code and modify it to your own mesh motion function, you can actually go to the your installation folder. And it doesn't matter that I have a version 2112, it can be any version. If you go to the installation directory, you will have a folder called SRC, which is called source codes. Okay. And within the SRC, you can actually search for this dynamic FVMesh file. And this will lead to dynamic FVMesh, dynamic mesh, FV motion solver, rigid body dynamics, and so on and so forth. So these are the mesh motion libraries that are already written within the OpenFOAM framework, and you can use it. All right. So particularly, I would suggest you to look into the dynamic mesh folder, and within that, there are different motion solvers. And also there is a library called 6 degree of freedom rigid body motion, which enables you to incorporate fluid structure interaction. Right. Now, the next part is, as you know that you now know how to set up the dynamic mesh stick and how to prescribe the motion and then how to change the corresponding boundary conditions in the 0 folder. Next is, how do we change the numerical schemes or numerical solution algorithms that are needed to get a converged solution for a moving body problem, right? So we need to adjust the solver settings according to our physics, what physics particularly we are trying to capture. And it is needless to say the fact that dynamic meshes have more stringent stability and accuracy requirement compared to the static meshes, because we are either deforming the meshes or we are moving one set of mesh in the other set of background mesh, etc. Now, during simulations with moving bodies, the boundaries or mesh or the domain will experience strong instantaneous acceleration, large displacement or deformations, and fluctuations in linear angular velocities. And that is the reason why we need more stringent stability criterion or accuracy requirement or higher tolerance value. Now, particular to the adaptive mesh refinement simulations, the meshes will change and the cells will become smaller and smaller, or they will, if we go for unrefinement, we will join different cells to get a bigger cells, etc. Hence, the cell volume will change. Therefore, if you are aware or if you have gone through any basic CFD course, you know that stability criterion named CFL number, or basically it is also called the Courant number, will change from refinement level to refinement level. So we have to include, instead of a fixed time step or a fixed CFL number, we have to include a adaptive time stepping or adaptive CFL number to get a converged solution. It's extremely important to control the CFL number and be sure that it remains within the limit of the stability. So if you are aware that most of the CFD schemes for like PISO, Simple, Pimple, we need a CFL number of less than 1, which leads to a converged solution. So we have to make sure of that case, otherwise our solution will diverge. Also, it is recommended to always monitor the mesh quality when dealing with morphing meshes and adjust the numerical methods, because if the cell deforms too much, the non-orthogonality or the skewness of the cells go beyond the set tolerance value, and that leads to the divergence of your solution. And of course, you can imagine intuitively that dynamic meshes are intrinsically unsteady. So we have to take care of the unsteady conditions of our CFD schemes. And they are computationally very much expensive. So I think this gives you a kind of big picture of how these moving mesh problems are different compared to the problems that you have done with static meshes. Right. So quickly going into the mesh morphing case, and so I will basically give you the brief overview of how to implement this mesh morphing and how to implement the overset method, and also with what kind of approach we take in these two different moving mesh mechanisms. And also I will briefly show you basically what are the other type of dynamic meshing case. So for mesh morphing, as I told, it's a mesh deformation case where we deform the mesh by moving the body. It's also known as mesh diffusion or mesh smoothing technique. Now we can define the functions by predefined functions or by including our trajectory or kinematics in the form of a table. And with morphing meshes, large displacement with large time steps will likely to result in low quality meshes, as you can imagine, because it will lead to a very large value of CFL number. Now, the time step also must be chosen in such a way that the mesh motion can be incorporated accurately with a converse solution. So not only the mesh, we have to also make sure that our time stepping is appropriate. Now, also when using mesh morphing, the solver will report the mesh quality. So you need to, as you run the simulation, you need to see how the mesh quality is changing as the body is moving. All right. So take a basic benchmark problem such as oscillating cylinder, the one I have actually shown you. So what are the kind of available functions that we can use within this dynamic mesh dict? So for example, I have taken a mesh as shown in the left, and the moving boundary is the cylinder where we actually apply the motion, right? So the base dynamic mesh dict will look like this, where we have the mesh motion library, which is mentioned as dynamic motion solver FB mesh. We have the motion library, which defines different type of motion, which is lib FB motion solvers. And also then we have different type of motion functions or motion libraries within this, and we are choosing here displacement Laplacian, and within that displacement Laplacian coefficient is chosen as a diffusivity case for inverse distance, and then we give the name of the moving boundary, which is cylinder here. All right. So this is a standard setup of how we set up the dynamic mesh dict. But here I'm just showing you a list of different type of solvers or different type of diffusivity methods, as well as different type of motion that you can incorporate here. Okay, so that's not the only option. Now, for example, if we choose angular oscillating displacement, it basically gives you a pitching kinematics, which is rotating. You can also set the pitching velocity by angular oscillating velocity. You can do oscillating displacement, which is like a translational motion. You can have oscillating velocity. You can also have time varying mapped fixed value, where you can actually kind of give a table with a time varying arbitrary motion if you want to. Okay. And there are different type of diffusivity methods also, and I will show you some visualization so that you can understand what they are. And this is a very important solver which is available, which allows us, which is move dynamic mesh, which allows us to actually see how the mesh moving even without solving the governing equation. Okay, so if you set up this case and you run move dynamic mesh, it will actually solve the mesh motion equation only, and will allow you to see how the mesh actually moving before you actually run the actual solver. Now, this is an example of how we give the more different motion functions, such as In this case, we are using oscillating displacement function. So I'm giving the amplitude, which is a vector. So the first one is the x amplitude, y direction amplitude, and z direction amplitude. So in this case, you can see we are giving an amplitude of 4, and everything is in SI unit. In the y direction, which is 4 meter, is the amplitude, and omega, which is the rotational velocity, we are giving as 6.28, which is almost like 2 pi. And the value uniform is a input so that we can visualize it in paraview, right? And in the boundary condition, as I said, within the zero folder, we change the boundary condition of the cylinder patch to moving wall velocity. All right. And then we choose different type of motion algorithms such as diffusivity function, etc., etc. And accordingly, we change our FV schemes or FV solution scheme to allow us to move the body. Now, this is an example of actually which I simulated exactly giving the function that I just showed you. So it is a prescribed motion where the cylinder is translating up and down with a given amplitude and a given omega, which in radian per second, which is the rotational velocity. Now, we can also incorporate, instead of giving an inbuilt function such as this oscillating displacement, we can actually give a table where we give the displacement value of the body with time and then tell the code to move the body accordingly. And this is how you can see first we are giving y directional displacement, then giving x directional displacement, then bringing it back diagonally. So this is an example of how you can incorporate arbitrary mesh motions. All right. Now, this is an example of how different diffusivity function actually changes the motion or not changes the motion, sorry. The motion is the same, but it changes the deformation of the mesh. So you can observe that with diffusivity function inverse distance, how the mesh is deforming from the boundary to the cylinder. And by changing it to exponential diffusivity function, the deformation type is changing. So these are very useful for incorporating very high displacement oscillations where we need to, without changing the non-orthogonality or the skewness of the cells too much. Okay. Now, we can also include multiple moving body. That's very useful. If you want to actually include 2 cylinders instead of 1 and then give different type of displacement function, this will be kind of another example where you can see in the first example, the 2 cylinders are moving up and down, and the second cylinder, the first cylinder is moving up and down, and the second cylinder is moving horizontally. Now, having said that, as you see that we are using deforming the mesh within these 2 bodies, we have to be very experienced how to make the mesh and how to change the solver setup so that our solution converge. Okay. Now, this is an example where we use a prescribed pitching airfoil, and we also use 2 tandem airfoils by using 2 different motions in the upstream and the downstream. We can change the frequency and amplitude of each of these airfoils in the motion function. Now, the last example on mesh morphing is a fluid structure interaction example where we do not define the motion function, but we allow the cylinder to move with the surrounding unsteady flow. And due to the aerodynamic force that the surrounding unsteady flow generates on the body, and we basically, this is, you can imagine it as a spring mounted cylinder, and we can study the vortex induced vibration of it due to the vortices set by the cylinder. So for that, the only thing that will change is the library function and the motion function. As you see here, we are using rigid body motion instead of the Laplacian library. Okay. And also along with that, because this is FSI, we have to have a structural solver, which in this case we are using symplectic, but it can be a Rangakuta method. It can be a Newmark beta method, which basically use numerical integration to solve the mass spring damper equation for this cylinder. Right. So again, I will come back to you if you have any questions, but due to the sort of time, I will first demonstrate another type of mesh motion algorithm, which is called overset mesh. Now, in contrast to the morphing mesh, in the overset mesh, as you can imagine, that the mesh is not deforming. Okay, so there is no deformation in the mesh, which allows us to incorporate a very high amplitude motion, because our mesh will not diverge due to very high skewness or high non-orthogonality. But in this case, we have different component meshes. As I told before, that in overset mesh, we use different disconnected meshes. And in this case, the example in the right, you can see we have a background mesh, then we have a refinement region, then we have a cylinder mesh. And in this overset meshes, we call them separately as component meshes. And there is a connectivity between these three component meshes, but they are not connected through the mesh, but they are connected through the solution in terms of interpolation between these overset surfaces, which are basically the outside surface of each of these mesh. And overset patches, this is very interesting that they can intersect with each other. So that can actually allow us to bring two bodies very close to each other, which is not possible by using mesh morphing. And however, the con is that overset meshes can add numerical diffusion to the solution. So as we all know that the interpolation is non-conservative, so this is comparatively less accurate compared to using mesh morphing algorithm. Okay. But there is a way in which we can reduce these interpolation errors, which is basically if we keep the cell size close to the overset patches, similar to the background cell size, that minimizes the interpolation error. All right. So as I said, there is a workflow of using overset mesh. We can actually generate different component meshes and then merge them. Then we have to define the overset patches where you can, which one you can see here in white dotted line. These are the overset patches where actually the interpolation happens. Then we have to assign priority, like the cylinder mesh here is the with the priority, higher priority, because we are actually interested to resolve the flow around cylinder. Then the next priority is the refinement regime, and the background mesh is the last priority. Okay. And then to solve this problem, we have to define a particular interpolation scheme and other related CFD schemes which are used by the code of the overset approach. So again, in another terminology, we name the three different cell types as whole, interpolated, and calculated. So the whole is the cells within this cylinder where we don't care about the flow and we don't solve the equation. Interpolated are the cells in the overset patches where the interpolation happens. And apart from these two, all the other cells are actually calculated where we need to solve the governing equation. Okay. Now, as I mentioned that for overset mesh, we need different type of interpolation schemes, and they change in terms of their accuracy and the intensiveness in terms of computation. So we have cell volume weight, we have inverse distance, least square, and we can try different interpolation technique and opt which one is the better accurate within the computational cost that we can afford to, right? So this is an example of prescribed motion, for example, that I have shown you before, that we have one disconnected mesh, which is one component mesh around the airfoil, and we have another mesh, which is background. So we do not have any refinement zone here. So we have only two different mesh zones. On the other hand, the next one shows you again the fluid structure interaction of a cylinder where we have two mesh. One is the mesh region around the cylinder, and the other one is the background mesh. There are different interesting features that we can implement in overset mesh, such as, for example, we can define a refinement zone and then move the refinement zone with our body, which is useful in simulations of different type of problems, such as you want to simulate a seed passively flying with your turbulent wind. Now, if you want to capture the flow around that, your computational domain has to be ideally infinite, which you cannot do. So what for that kind of very large computational domain, we cannot afford to have very fine cells all throughout the domain. So we define a separate refinement zone around the body that we need to capture, and then move that refinement zone along with that body. Right. So with that, I think I will take 5 more minutes to kind of show you what can be the other different type of dynamic meshing techniques. So the next one is moving meshes. And this is an example where we move the whole domain itself. Okay. And if you can intuitively imagine the application of it, and the major application of it is a problem like sloshing. For example, if you have a oil tanker moving with a tank filled with oil, and with the motion of the truck or the tanker, the oil inside that tank actually moves, and it creates a fluid structure interaction, particularly if the container boundary is not very rigid. And they create a dynamics which is called sloshing, and it can be also seen in other type of problems, but this is one that is coming to my mind in this respect. So you can here, instead of moving a particular mesh region within the computational domain, we can actually use this rigid body or the rigid body motion to move the whole domain. And the library for that is called the dynamic motion solver mesh, and the motion solver is the solid body. And within the solid body, we can use axis rotation motion, linear motion, multi-motion, rotating mesh motion, ship dynamics, 6 degree of freedom, etc., etc. Okay. Next one is the sliding mesh that I have already told you, which uses an arbitrary mesh interface to do the interpolation, at which one region of the mesh slides over another region. So in this example, as you can see that the inner rotating zone slides over the outer static zone, and thus we incorporate a pitching motion in an airfoil. But in this case, we have to use appropriate boundary condition, which would be the boundary condition would be cyclic AMI. And we have to define two different patches which are neighbor to each other. Okay. And then we have to kind of like say or actually declare that this is the AMI patch 1 and the other one is a AMI patch 2, and they should interact with each other to interpolate the solution back and forth from one mesh region to other. So the last type of adaptive mesh, the mesh moving mechanism is adaptive mesh refinement. As I said that in this case, particularly the mesh divides themselves into smaller cells, or they join to make a bigger cell depending on a refinement criteria. And that refinement criteria is based on a scalar field that we want to track, and which is named here as quantity of interest, which is the physical quantity that we want to track. And then we can actually give tolerance criteria such as what will be the size of the smallest cell, or what would be the maximum cell size, etc., etc. And this is an example of a dam breaking example, kind of, where you can see the refinement actually captures the water level, which is alpha water, which is the volume fraction of air and water. And by capturing that, we can capture the interface of that. And the dynamic mesh dict here looks like something like that, where we have to define the field as alpha water, and then other control parameters like what will be the maximum refinement, what will be the maximum cells, etc., etc. And important part is that in this case, we have to correct the fluxes and check for the tolerance criteria at every iterations. With that, I stop my presentation here and happy to answer if you have any questions. So I can open the chat, but if we have time, anybody wants to unmute themselves, please unmute and ask me. Right. So basically, moving mesh and dynamic mesh have different motions or same. They are the same, basically. If we are moving a mesh, we call the case becomes dynamic. That's why we call them dynamic meshes. So this dynamic mesh can be a component of the mesh, can be a cell zone around a patch, or they can be the whole computational domain, as I have shown you. Right.
Sir, is learning Snappy Hex Mesh enough for OpenFOAM? Do we have to learn any ICMCFD or any other software?
It depends on the problem that you attempt to capture. So Snappy Hex Mesh is good enough for even in very 3D complex meshes, but it has known issues in capturing the boundary layer very well. For example, maintaining the Y plus distance or the first cell distance over the body. And this is all becomes important if you want to capture a very turbulent flow, right? And you want to basically resolve the flow to a very small scales. And in those cases, Snappy Hex Mesh might not be the best option. So you might want to use a bit more sophisticated mesh.
So what is the next available option?
If you want to go for open source option, as I said, you can try to learn Salome Mecha. It is a very sophisticated open source tool which allows you to do a three-dimensional meshing. You can learn GMSH, which is again an open source thing. But then if you are already having licenses of softwares, commercial softwares, you can go for ANSYS Fluent Meshing or Pointwise, which is very sophisticated. But this now belongs to Cadence, which is basically has some license cost for it. So I see there are some more questions in the chat. Which dynamic mesh method useful to solve boiling flows or combustion? Again, I mean, as I said, any of these dynamic mesh methods can be implemented depending on what you want to capture. I think adaptive mesh refinement is a very popular approach for combustion system, because if you want to basically capture, for example, flames or other things, you can set the quantity of interest and use adaptive mesh refinement. For overset grid, how difficult it is for a geometry with full of curvature or distinguish between the whole interpolated calculated cells? Yes, this is a very important question, because yes, it is difficult unless you actually define the mesh in a way that the cells are very much refined around those features, such as, roughness, or such as holes, etc. So your mesh has to be very fine to actually appropriately capture those changes in your surface. But in terms of dynamic meshing technique, there is no problem, as far as I understand. Next is for complex analysis like turbo machinery analysis. What type of mesh will be a good fit? I think for turbo machineries, a lot of people use this sliding mesh technique, such as using arbitrary mesh interfaces where you can slide one mesh component over other. Let me move to the next question. Can we give some idea on hypersonic intake FSI? Now, these are very specific applications, and I think that's not the motive of this workshop. You can talk to us separately. We can help you with that. After importing geometry from ANSYS, is there any use of block mesh dict file? No. If we incorporate geometry or mesh from ANSYS. Now, what do you mean by geometry? If you incorporate just the geometry in terms of STL file, you have to use Snappy Hex Mesh to mesh it using that STL file. But if you incorporate the whole mesh, you do not need block mesh dict, because you already will have the polymesh folder. Okay. So can you please repeat other open source mesh apart from Snappy Hex Mesh? One is GMSH. I'm typing in the comment. One is GMSH. Another is Salome Mecha. So these two are very powerful open source meshing tools. Can both generate structured mesh? Yes, Salome Mecha and GMSH both can generate structured meshes. Okay. How to implement an appropriate momentum source term in Navier-Stokes equation? Etc., etc. So for that, you need to rebuild the solver and modify the source code of the solver and recompile it. And I think I have some tutorials in my YouTube channel, but again, we don't have time to demonstrate to you how to do that now. Thank you.